Hi, last but not least, thank you for the remaining heroes. So I'm Nufar, I'm from Intel, and I want to start by answering 3 questions that you are wondering. So yes, we're doing machine learning at Intel. Yes, Intel is here to stay. And yes, we're hiring, so you're more than welcome to send CVs later. So I belong to a team called Advanced Analytics. We specialize in providing machine learning and big data solutions for the global Intel, not just Israel. Though we're a proud Zionist, we have all our employees here in Israel, about 100 guys. 30 of them are data scientists. The rest are big data developers and product and data analysts that are doing some very cool work for Intel. 3 main vectors of solutions that we create. First of all, are solutions that solve large problems at Intel, things that machine learning and big data can make a true difference in. Second, we do some work outside of Intel to leverage these capabilities to create new solutions or new capabilities for Intel. And the last, Intel is a hardware company. Machine learning requires a designated hardware. We help them to create the requirements for the new machine learning hardware that Intel is producing because we're the subject matter experts. So I want to tell you a story about a solution that my team created, the one that I'm very proud of. It belongs to this class of solutions. It is an internal solution for Intel. Just a few words about me. I manage a team that creates machine learning and big data solutions for the R&D organizations at Intel. We work on quite a lot of problems per year, creating the solutions and moving to the next problem. I'm a Ben-Gurion graduate, so it's always fun to come here, and I love the people, and we hire them in large numbers. So as I mentioned, we work on many problems each year. I just gave a few examples. We work on a surface fitting to help project design parameters with active learning because creating samples is very expensive, so you need to do a very smart selection of what to sample. We're also doing some very cool work around embedding machine learning algorithm inside the chip to make an online decision as to various power decisions, what to turn on, what to turn off, what budget to do, and many other things. But I wanted to talk about the last one, a big problem in R&D for Intel. It requires a pattern recognition, and I'm going to talk to that in depth. Okay, so about the problem statement. When you validate hardware as opposed to software, you have endless number of functionalities and states you want to validate. So it's impractical to create a designated test for each and every functionality that you want to validate. So you can pinpoint a handful of, and when I say a handful, about thousands of specific functionalities or states that are critical and you want to validate. And as for the rest and all the cross between those functionalities, you have to rely on large random tests. And when I say random, they have to select between thousands of test inputs, thousands of code segments, and the assumption is if you run enough random tests each and every week and throughout the life cycle of a hardware validation project, you should be able to validate most of those critical functionalities, and you can take the product out and make sure that it's good enough, robust enough, and can cater for the various needs that an Intel processor has to cater. So the world that we're dealing with is a world that is doing a fair job for most of the functionalities. And when I'm saying a good job, that means that the tests need to find the existing hardware bugs and need to find them fast and efficiently. So obviously we like, in a kind of a opposite way, we like tests that fail, because that means that they kind of bumped into an issue with the hardware, and those are the good ones. But what happened for tests that are passing? Can we make sure or be confident that our hardware is bug-free and we can go ahead and release it to the market? Not necessarily. We are quite sure when we validated a specific functionality many times, because we know that if we had to cross it with other functionalities or reach a specific state, if we been there enough time, that means this functionality is probably good and we can go ahead. But what happens if you have a functionality that is not being validated very frequently? It only happens a handful of time out of the many, many, many thousands tests that you run. Is it good enough? Maybe there are corner cases that you haven't validated. Can you go ahead and make sure that this is a bug-free area? And the answer is not necessarily. We know that when you have a functionality that is not being validated enough, it in many cases hides bug. So what do? You have the random test. You have the many thousands of test inputs. It's not working enough. It's not validating those hard-to-validate functionalities. The answer is, of course, because we're here talking about machine learning, do it automatically. Create a test or select the test inputs that will validate those hard-to-validate functionalities in a smart way. And then you can go ahead and say, if I haven't found a bug, that means that this area is clean. And if there are bugs, if I create tests that are targeting those functionalities, I will be able to uncover them. So this is the opportunity or the problem statement. And what we did, we take the data out of those many, many thousands of random tests being run each and every week. We ingest them to our system, do a very nice pattern recognition that I'm going to explain in a minute to identify what are the test inputs that are critical for validating those hard-to-validate functionalities. And then what we do, we automatically create new tests that are being run on the hardware and boost the quality of the test and find the bugs should they exist, or at least give us the confidence to put the product in the market because it was clean from issues. So this is just the overview of the solution. Naturally, I want to go into some details here. So how does our data look like? And here I'm going to give you an example of data for one specific functionality. We do this for each and every functionality that we want to target with those new machine learning-based tests. So we get a test recordings that is comprised of three main parts. The first are configurations that are being determined before the test even began. In what kind of atmosphere or setting the test is going to run. And again, this is something that is being selected randomly out of a very large set of options, hundreds to thousands of configurations that can be used. And then we are getting the actual test recording, where each letter here represents a code segment, again, being selected randomly, that was actually run on the hardware to validate it. And then we get an indication whether the desired functionality, the one that we're after, was validated. And the star here indicates that this is a test that was able to validate this functionality. So the graphic here are a little bit confusing because it seems like we have many positive examples of tests that are able to validate the required functionality, when in fact we have a very small number. You can see here between 10 to 200 positive examples of tests that are doing what we are after, examples to learn from and train our algorithms. And we have many, many thousands of tests that are not validating the functionalities. Highly imbalanced problem, not a theoretical, a very practical and very imbalanced problem. Okay, so I guess you could get a feel or a sense of our challenges, and we had many of them. I wanted to highlight the main three and explain how we handle each and every one of them. So why don't I go and start with the imbalance issue. As I mentioned, 10 to 200 positive examples versus many thousands of negative examples or tests that are not doing what I'm after. And you can see the percentage. It's a very low, 0.02% of positive examples. So we addressed it in three directions. The first two, what we did, we started with a massive downsampling. For each positive example, we randomly sample 100 negative examples, then we eliminate all the rest. And then, you need to understand that the question that we're trying to answer are which test inputs are the one most critical to creating a validation of a specific functionality, for creating if you will, a hit on this functionality. So essentially, we're not looking for a good classifier to be able to classify. We're looking for the features that enable us to create the good classifier to distinguish between tests that are validating this functionality and tests that aren't. So we ran several classifiers. A very good one from a results perspective was the random forest algorithm. And then what we did with the algorithm, we did an inference on the feature importance of the random forest, and taken the top features that are enabling us to classify correctly between a test that is validating a specific functionality to a test that isn't. So this is one solution approach. Another one is a more classical filter approach. We utilized correlation, and correlation worked well, so we didn't do other things, but it's not. We did a correlation between the label of validate versus not validate to the various features, or a correlation of groups of features to the label, and identified the one that are mostly correlated to positive examples, to being able to validate the functionality, because again, this is what we're after. The features that are, should we select them, will create a positive label. So these are two examples. The last approach, we didn't do downsampling. We simply went with the algorithms for frequent item set mining. And again, because we're only interested in the positive examples, we utilized recall as the objective function. We're looking for sets of items or sets of test inputs that create a large, good enough recall for us to be able to correctly identify what will end up validating the functionality. So we have these three solution approaches. We create an ensemble of solutions out of these approaches. So we're all good and fine here. But I guess you can sense the magnitude of the problem. Everything I was talking is for one specific functionality. We want to be able to solve it for many different functionalities, and over that for many different users. That means that our scale, or the amount of data that we need to ingest and process, is very big. So naturally, we had to go big data. And we went for a Spark-based capability. You can see like a scheme of the architecture. We are able to ingest through a very persistent API, one that always listens to whatever validation work is being done and sends us log files our way. We do some processing on the data on the fly using Spark streaming and store it in an HDFS. And then the actual algorithms are being run utilizing Spark. These provide us some very good starting points using ML and MLlib. But in some cases, we had to create our own algorithms in Spark. And I didn't mention, but some of my guys are here. So if you want to catch them, this area, if you want to talk to them a little bit more about the fun they have with Spark, and it is fun, then by all means. And then after we create the algorithms and the result, we broadcast them back to the users. New tests are being run, and of course we learn from the tests that are being run to be able to tune our algorithms, to evaluate, and to be able to tell the whole world, because we're not doing a pro bono work, how good a job we're doing, and be able to show them that it is something that brings true value to our internal Intel customer. So last, it seems all good. We had a good algorithm. We had a big data solution that enables us to run it. But in fact, one of the largest challenges was to evaluate the results. We did the traditional cross-validation, created a list of results coming from our ensemble of algorithms, and then what we did, we ran them through actual tests. We created the new test, and we anticipated that good models that scored good in the training will be good in real life. And then what happened? In many cases, the greatest models didn't get a good result in the actual test. Why? In many cases, we know that there are probably hidden parameters or hidden inputs that we are not getting into the algorithm, and they probably have a very significant impact on what's the actual outcome. So what we had to go and do, kind of a reverse engineering, and identify during the training which measure had the most correlation to the good results, and then go back to the algorithms and do the selection based on the most correlated measure. For us, it was F measure, and it's not perfect. In many cases, we are not, when we predict that we're going to have a very good result, it doesn't come that way, and in others, it happens the opposite way. But don't worry, we have very good results. We are able to increase significantly the amount of validation per each and every functionality that we target, and more importantly, we do uncover new bugs. So our customers, all they care is that give us more bugs and do it very quickly, and that we are able to do. I'm not going to go into numbers, but I promise you that we're all happy about that. And we have so many new direction, or it's still a work in progress. We have many ideas on what can be done to improve this. For example, we have big data, we can go exhaustive. We don't have to do those heuristic approach. So we're working to try and do a much more robust approach. And also we have some ideas on how to utilize text mining approaches to solve this problem, even it's not a typical text mining problem. That's it.
Thank you very much.